Okay, so we have seen, we did the computation before that this, for quartics, then the moduli space is 19 dimensional, and that you can do a lot of very similar computation in the case of complete intersection and double planes. And so why only 19 moduli? It's a remark. Why we find only 19 moduli? So because omega on this O lambda K3 parameterize all K3, as I say, also the non-projective one. And remark that if S is projective, then you have an embedding let's say phi from S to Pn. That was a. So this means that on S we have an ample divisor given by the hyperplane section. Which is L equal to S intersection H, which is H in P3 on hyperplane. With L square equal to D for some D, depends from the embedding you have to consider, for some non-negative integer D in Z bigger than 0. Okay, 2D, because if you remember the K3 lattice is even, and of course this class is in particular a class of H2 SZ, okay, which is an even lattice, so it's 2D. So that omega S, the class, let's forget about the marking for the moment, belong to the following domain. It is a set of omega in P of, well, we understand this a bit better in a minute when I will talk about Nèron-Severi group and transcendental lattice. So the period, but anyhow, remember that omega S live in H2 0, okay, which is orthogonal to H1 1, and L live here inside, and even more in H1 1 in let's say maybe even more in H1 1 with H2 SZ. Okay. So omega live in that space, which is L perp, where the perp is in the K3 lattice, tensorized by C, such that omega bar is positive and omega square is equal to 0. So L perp is the orthogonal complement, is a set, let's say, of V in lambda K3, such that Vx is 0 for any x in L. Okay, the orthogonal lattice. And then you see that you lose one parameter, because this is just P21. You take something of dimension 1, you take the orthogonal complement, you take then something, it is 22 dimensional, projective is 20 dimensional, and I have one equation, so it is 19 dimensional. And for example, sorry, I brought P3 because I was thinking about quartics, but it's Pn. And so, for example, I was thinking about quartic, what we were talking about before. You put a quartic is in P3, you cut with an hyperplane, you get a quartic curve, another hyperplane, you get 4 points. So in that case, D is equal to 2, and L squared equal to 4. So all quartics, the period point of quartic, live in this space. So in P of L per with L squared equal to 4 and the condition. And this is 19 dimensional. So this is how somehow the 19-dimensional space that parameterizes all quartic K3 surface. And then you can do the same, for example, for double plane. Well, double plane is maybe not a good example because I need the sun embedding, but let's say complete intersection of type 2, 3. There you can compute the polarization as square 6. So then you can live in that space with square 6, and then again it's 19 dimensional. So you have different strata in the modular space parameterizing your projective K3. Okay, I will maybe say something, some very few words a bit later when talking about projective model of K3. And again, we'll see some example. But now, well, I was talking very often about actually this space, which is the Nèron-Severi group. So let's recall the definition and see what happened again for K3. So Nèron-Severi group and transcendental lattice, just to recall some fact. So let's take SK3, but actually what I'm going to say at the beginning is you can just consider a compact complex surface and consider the exponential sequence. So you have Z, and then let's take an notation OS. OS star, 0. It's actually of analytic sheaf. So here I have the constant, and here I send F to E to Pi F, which is never 0. Think now cohomology. Okay, so just a part of that. H1S OS. What's the good part? Let's say maybe H1. Yes, it's good. H1S OS. Then H1S O star S. And then H2 SZ. And so on. It's part of the sequence I'm interested in. So you recognize here the Picard group. This is another description of that. Okay. And this map is known to be the first Chern class. To associate it to a line bundle is first Chern class. So C1. So to L associated C1 of L. So let me just say something in general, and then actually I will go to K3 where this is 0. So you see so this map is in general a kernel, which is denoted by peak 0. And so peak S modulo peak 0S can be identified by with the image of C1 or delta. Well, yes. Well, I call it C1, which is in H2SZ. Okay, and this is what is called the Nèron-Severi group. Which is denoted often NSS. But for K3, you don't have to care very much about this peak 0, because you know that H1 SOS is 0. So the difference between Nèron-Severi group and Picard group, there is no difference. Okay, otherwise, one can see this as divisor modulo of what's called algebraic equivalence, and peak of S is rational equivalence. But for K3, as we started with that, we have that H1 SOS is equal to 0. So this is true also for all surfaces where the H1 is 0. So that the Nèron-Severi group peak S is equal to NSS, and we define NSS. And NSS is in H2 SZ. In here is the structure of a lattice that comes from the lattice structure here. Is a even primitive sublattice. So primitive sublattice, well, you should worry too much about primitive for the moment. This means essentially that I put it here inside, and the quotient of the space by the image is free, so there is no torsion. Okay. Maybe I will say something more about primitive sublattice a bit later. But the important fact is then that you have line bundles that you can see also as class in the Nèron-Severi group, and this is a lattice. So again, you see lattice theory come also into play to this. And the orthogonal complement of NSS is also lattice, which is called the transcendental lattice. So the orthogonal complement of NSS in H2SZ is also a lattice. So then that I will denote, well, there are many TS. So this is I just write in this way, even if it's maybe redundant. It's called the transcendental lattice. And one can also see by Lefschetz theorem 1-1 classes. So one can also describe the Nèron-Severi group that I was writing before. NSS equal peak S equal the H11, and here take the integral point. Okay, so this is very useful because I give you also a description, if you want, also as the set of the X in H2SZ, such that if I do the product with the two form, it is 0. So one say that this is also omega S perp in H2SZ. You have different descriptions. This is actually very useful depending on the situation that, on the problem you are studying. Let's also think about the signature of that. So that's why during the rest of the lecture, I will often, even if I will try to pay attention, I will often talk about Picard group or Nèron-Severi group. Just one of the two is equivalent, so that does not make any difference. And about the signature, of peak S, let's just think about the following fact that maybe help you to see the things. Well, first of all, we know that rho, which is a Picard number, is the rank of peak S, or Nèron-Severi, which is called the Picard number. Of S. So rho, sometimes one say also rho of S, depends on the notation, but rho of S is less or equal when it's live in H2. So first of all, well, let's think about that. So H2 is rank 22, but in fact it lives in H11, so that rho S is less or equal than 20. Okay, so it could be maximum 20. And observe now the following fact, if you want to give the signature. Following. So you remember that we had H20 plus H02, which is orthogonal to H11. Okay. And we know also that the signature of H2 SZ is equal 319. Okay, this is generated by omega S, and this is generated by omega S bar. Now consider the real classes. The following. Or better, the real vector space. V, which is the span of omega S plus omega S bar, which take another one, E times omega S minus omega S bar, which come from the real part and imaginary part. So this is two-dimensional. And if you look at your bilinear form on that, and we have just a computation as we did before, we have that omega S plus omega S bar times omega S plus omega S bar is positive, and also the other one. Okay, so that just to tell you that you have two real classes that live here inside this real space, and not here. So this means that the signature of peak S could be at most one something, okay, but no more than one, because I have for sure two classes given by the automorphism form, which is real, on which the bilinear form is positive. So it somehow kills two of these three positive eigenvalues. And so let's remark also that S is projective. So if S is projective, let's say, then, as we remarked before, there is L ample class with L square positive. So this means that the signature, so hence this all together, we have that the signature of peak S is equal to 1, rho minus 1. Rho is the rank of the Picard lattice. And so the transcendental lattice has a complementary signature, which is 220 minus rho. So that the signature of transcendental lattice, so noted by TS, is equal to 20 minus rho. Okay. So these are two lattices with this signature, and this one, as I say, comes from the fact that we fixed this ample class. Remark also that that in fact, so the transcendental lattice is defined as this orthogonal complement. So if I look here, so in fact, TS tensor C, if you want, contains this sum. Okay, so this means that independently of this computation of the signature, tells you actually that the period of your K3 move in the transcendental lattice, tensorized by C. So if you remember, for example, when we were talking about quartic, I was telling you, okay, you must parameterize quartic by taking the orthogonal complement of the polarization and let moving the period. So this means you let move the period in the transcendental lattice, which is then, in that case, rho is equal 19. So this is quite a big dimensional. So sorry, rho is equal to 1. So this is transcendental lattice is rank 21, and so you find the 19. So the period move there. So that's why transcendental lattice and Nèron-Severi lattice have important application when you study K3. And in relation to that is maybe a good point to say just one word about projective models. As I said, so once you fix the polarization, then you can describe what is the moduli space. Let me see on the blackboard, but let me write again. So if S is projective, then omega S, as I say, belongs to P of, let's say, TS and put a small l here, tensor C. It's not there, this is L perp. Actually, what I wrote there, so, but I need again, so I'm sorry I write it again, just to not make too much confusion. So I leave that space. Omega bar is positive. Okay. So TS is the orthogonal complement, so it's the transcendental lattice of a projective one. Okay, it's the transcendental lattice of this K3. So generically, S in Pn has, this means also depends on how this is done, has a Picard group equal to Z times L. So you have only the hyperplane section. Actually, this is confirmed, if you remember, by doing the moduli computation. So the rank of the transcendental lattice is the complementary of the rank of the Picard group. And so this means that generically for a point here, so the Picard group is exactly generated by the hyperplane section, and I have nothing more. So L squared equal to D. And recall at these points I'm projective model. well, the notion maybe of polarization. Since I was talking about this modular space, so a polarization on a K3 surface is an ample line bundle L on S, like here. For example, in that case, we take the hyperplane section is even very ample. And let's describe some kind of useful the following theorem due to Saint-Donat. So it was Saint-Donat. In the 80s, there is a very famous paper where he started describing linear system on K3 and projective model. So the interesting fact is that we have seen that any time that I have a K3 with this polarization, then belong to that modular space. For example, if I have a quartic, then it belongs to this. Well, the converse is also true, of course. And so let's see the following theorem. So take H, a line bundle on a K3 surface S. Okay. Take H, a line bundle on S, with A square positive, and assume that H has no base component. And then this was shown by Saint-Donat. This is not trivial, but this means that also has no base point. So this was always shown by Saint-Donat. Then we have the following possibility. So we have a map. Let's say phi H from S to some projective space Pn, where n is equal to the dimension of this H0 or SH minus 1, that when you want to apply the Riemann-Roch for K3, this is a half H square minus 1. We have a map. Oh, sorry, no, it's not an embedding. I will just an embedding. We have a map such that either phi H is a 2-to-1 cover, and the dimension of the image, the degree, a half H square, or the other possibility is that phi H from S to Pn is birational, and the image has degree H square. So the first one is called the Hyperloop Decays. So birational because in that case H can contract something. Okay, so for example, if H is bigger than F, it can contract minus 2 curves, and the image can be singular. So this is hyperelliptic. Case. And in fact, we have seen example in both the cases. For example, if you take So let me just recall then the projective models. So some examples. So if h square is equal to 2, okay, so you can think about curves, for example, h as a, for example, take as an irreducible curve. Then something like h square is equal to 2 tell you that you have a double cover to P2. And well, are the K3 double plane? So what we have seen. So it's clear that it's hyperelliptic cannot be the second one because, well, in that case, I go to S to P2. So it cannot, and S is K3 and P2 is rational. So that is clear that it's hyperelliptic. So take, if h square is equal to 4, and say it's not hyperelliptic, okay. Well, this is the case exactly when you have phi h go from S to P3. So this is quartic. This is the case. And then h square equal to 6. Again, not hyperelliptic. Then phi h give you the embedding of S in P4. It's complete intersection, 2, 3. And h square equal to 5, not hyperelliptic. So hyperelliptic case can well happen. Yeah. So just to see again from another point of view what we have seen at the beginning of the lecture. Then S is in P5, complete intersection of kind 2 to 2. Okay. So this is the image that you have. And generically, so the Picard group of these surfaces is generated only by the hyperplane class. So that's exactly that square. And in fact, there are, when you study, for example, projective model of K3, you start studying divisor like this. So you just ask that the square is positive. And then, for example, you start to understand if it is ample or not. And then studying projective model. Okay. And then, of course, one can give also example for higher T. Okay, so all right, so I could talk much more about projective model, but it's not the aim of the lecture. I want to go now to automorphisms, start to talk about that. Which is concave surfaces. And then you will see, well, we will often come back to projective model and they are very useful, in particular when you don't want to give an example, in particular that form. And we will see how Torelli is very important in that case. Okay, let's now go back to SK3. For the moment, again, projective or not. At least for the moment. Then I will go back to the projective setting. So as I said, one wants to study the property of the group of automorphism of S. So that gives you a lot of information on the surface. Or let's say sigma, maybe, change the notation. Sigma will be a holomorphic map. One wants to understand property of the automorphism group, but say this can give you a lot of properties also of the surface. First of all, we have a map, just to resuming what we were saying until now. So we have a map. Actually, this comes somehow from Torelli. They go from out S to the isometries of the K3 lattice. Or let's say H2SZ, where I have all the, let's forget marking or not marking. Well, we associate to sigma star. And this map I denoted by capital Phi. Then, thanks to Torelli, we can describe the image of Phi. So, thanks to Torelli, image of Phi are the effective Hodge isometry.
I don't understand the examples on the right if we apply, because if X squared is 2,
yeah.
That means like because n is X squared divided by 2 plus 1.
Yes, this is the degree of the image, it's P2. It's just it's surjective over P2, and it's a double cover of P2, ramified on a sextic. For example, if you take A squared equal to 4, and they have hyperloop decays, the image at degree 2, and in fact is a cone, so you have a double cover of a cone that ramifies somewhere.
Is the dimension of the angular space and the problem is because
sorry, you have a problem with the
dimension of the space in which it arises?
The degree. I don't know, it's the degree.
Because when we do the canonical map associated to the line boundary,
yeah.
we say just like n is X squared on 2.
Ah, sorry, yeah. Yes, sorry, yeah, sorry. Ah, sorry, yes, thank you. Yes, I wrote -1, but it is +1, sorry. Thank you. Sorry, of course it's +1. Otherwise it does not work, not even in all other cases. So also for P3, you have S squared equal to 4 divided by 2 plus 1. Sorry, yeah. Thank you. Okay. So let's go back. M of Phi, what are the automorphism, are isometry, so are the effective Hodge isometry. Okay, so that are those that send the 2 form to the 2 form and a Kähler class to a Kähler class. And moreover, this map is injective. Moreover, one can show that phi is one fact about this map is injective. For example, if you go, some of you maybe are working on hyperkähler manifold, which is the higher dimensional generalization, one of the possible higher dimensional generalization of K3. Well, if you take deformation of the Hilbert scheme, this is true, at least for HILP2, but this is not always true. For example, for generalized Kummer is not always injective. But it is the case for K3. This is very good because then we can really identify out S with that one, with that image. And again, you see the study property of the image will give information of the automorphism. So more properties of out S. So out S is discrete. So essentially one can see that as an algebraic group of 0 dimension. So it is a discrete. Then this is a big result. Out S is finally generated. This is a paper of Sterk, but he did, I think, also the projective case, and then Ogiso studies also the non-projective case. And let us think about the following result, that in fact, if you take a generic K3, so something like in the example, but generic, then except this first case, where here you have something which is called the covering evolution. We come back to that. But in all the other cases, we take generic one, then the automorphism group is trivial. So you have nothing more. We have the following theorem. So let S in Pn generic K3. So this means that the Nèron-Severi group or the Picard group of S is ZH or Z. Sorry, I change always the notation, but in any case, this is the hyperplane section. H square equal to D. Then out S is final. Is trivial.
We can't read. Sorry. Theorem, the first line.
Let S in Pn be a generic K3, and so a generic. Yes. And then I assume that the Picard group of S is generated just one by the hyperplane section, ZH, such that H is the hyperplane section and H square is 2D. Then out S is trivial. I have also to say for D different from 1. Because as I say, D equal to 1, we will see in a minute. As a corollary after that, if D is equal to 1, H squared is equal to 2. This is the example I was given before, and it is the double cover of the plane. So you have an automorphism on that comes from the covering evolution. So let's give the proof of that. So it's an idea of the proof. Because if you do the proof, you go to you need some result on algebraic groups. So first of all, observe that if sigma is in out S, since you have this condition, and sigma preserve the decomposition, in particular send the Picard group to the Picard group and the transcendental lattice to the transcendental lattice, we have that sigma star of H is again is preserved somehow. It's more, I send an M-pole class to an M-pole class, okay? So send since the Picard group is a Picard number 1. And since it preserves an hyperplane section, so this means, so you are in Pn, and actually this H gives you the embedding. So let's write here. Then the automorphism comes from an automorphism of Pn, because H is a hyperplane section. So H is a linear system that gives you the embedding, so that the section of this of this linear system gives you the coordinate somehow of the space, and this is preserved. So since it's preserved, then sigma is induced by an automorphism of Pn. Let's say sigma, just to not use too many notation, is in PGL PGLN, or n plus 1 might be always I think. Okay? Yes? Sigma star H is preserved, so it means it's sent. So the hyperplane class is preserved. Yes, that's all. Ah, sorry, yeah. Then, sorry, yes, thank you. So then, sorry, I'm getting tired. H is preserved. Thank you. That's correct. And so is induced by an automorphism of Pn. So it lives in that group, but not only. Since it preserves an M-pole class, okay, it preserves also a Kähler metric. Or let's say a Kähler metric. Okay. So in particular, it preserves a metric. On the space. So this means that out S, so hence, out S is a discrete, let's say Lie subgroup, because I'm talking about algebraic group. Subgroup of a compact Lie group. Okay, don't worry too much about that. I can. So discrete, well, we have, it's one of the factors we were writing before. Compact because well, PGL. So this is not compact, but if any time that you preserve a metric, then it becomes compact, like orthogonal matrices in invertible matrix. But then it's finite. This is the first step. So this is actually, this first part of the proof is quite useful. Again, it depends on what you're working on, because anytime you find an automorphism that preserves an M-pole class, well, this is the argument to say that it has finite order. That's quite useful. But let's go on with that. So I have still some minutes. So now we have to study finite automorphism of S. And well, I have to anticipate some result that we will use after that. So we have to study finite automorphism of S. So we have two cases. If the action of sigma on the two form preserve completely the two form, so this means we'll see in the definition in a moment, sigma acts symplectically on S, then one can show, and we will see this later, that the rank of peak S must be at least 8. So actually this case is impossible because the Picard group is 1. Here, since rank of peak S is equal to 1. Second possibility, so S sigma is not, does not preserve the form, is not omega S, so this means, we'll see again that later, that there is a constant factor coming in front of omega S. Then, again, about some consideration on the rank of the Nèron-Severi group on the transcendental lattice, tells you that I cannot write down everything here, but well, let's say maybe I can write down, however. Then, if order of sigma is bigger than 2, we have, again, I'm just stating something that maybe we will see later, that the rank of peak S is strictly bigger than 1. And again, it is impossible here, because the rank is 1. So that, so sorry for not giving much more details here, but it would take a long time, and maybe we'll talk about that later. So that only involution are possible. Okay, the only involution are possible. But here again, we will see that if Picard rank is 1, and you have an involution, but again, by general study of automorphism of K3, then would say that h squared is equal to 2. Again, sorry, there are some more details, 3 points that are not completely clear, but you need some result on automorphism that I don't want to give now, maybe later. So 2 about the rank of the Nèron-Severi group, the Picard group, that must be big enough to have automorphism of pi order, except for involution. But then when you have an involution and Picard number 1, then you know that you must be in that case and not have something more. So that out S is equal to identity. In all that cases. And let's just formulate the corollary and then I will stop. What happens if h squared is equal to 2? It's a very similar argument. Maybe I will not give the proof. All right, take S, again, generic. Or take just SK3. Pick S equals ZH. H squared equal to 2. Then we know that when we discuss projective model, that S is a 2-to-1 cover of P2. And out S is Z modulo 2Z generated by iota, where iota is the covering involution. So anytime you have a double cover like this, you have an involution. which come from you switch the 2 points in the counter image, and this is evolution. So iota, the covering evolution. Okay. Well, the point here, I will not give the proof, so it really follows. Actually, immediately I say a corollary because one need the argument in the same way as the proof. First, one think about that, well, S is projective, so you put in some projective space, and you can show that the automorphism group is finite. And then you have only non-symplectic involution, but you cannot have more than one, because if you have more than one, you get a symplectic automorphism on that, and then, well, this is not possible. So one can show that in that case, really the automorphism group is the only case where K3 is a genetic projective and the automorphism group is not trivial, is exactly that one. In the other case, you have nothing. So you need a higher Picard number to get automorphisms. Okay, we'll stop here.